Hey everyone, how's it going? I just wanted to today we're going to be talking about sorry about that. Today we're going to be talking about magnetic fields. Um, I'm a Amperes Law associated with that, and the magnetic force between two wires when they're sitting next to each other. So let's get going on that here. So before we get too deep into that, it's important that you understand the right hand rules here. So let's talk about the right hand rules before we get going into anything else. So the right hand rule, there's two of them. They're essentially doing the same thing. One of them is supposed to, they tell you, is describing a coil, and the other one a hoop. A hoop, which is a coil, and then a long wire. But essentially, they're the same thing. Okay. So the first one tells you that it essentially says, right, to find mag field with known a current direction. Okay, so if you know current direction, you can get the magnetic field with this right-hand rule. So the first thing you need to do is put your thumb in the direction of current. Okay, if it's a right. So like I said, this one's, they say it's for a wire, but actually you'll see how they're kind of interchangeable here. So don't forget, before we do this right-hand rule, just let me remind you real quick before we do that, because this is important as well, is just remember how a magnetic field looks. Okay, we talked about this at the beginning of the chapter, but just remember, right, it comes out of the north. Oops. Comes out of the north, goes into the south, right, and then back. So it's circular, right, and then it goes from the south to north inside there, right? But it's circular, right? The magnetic field has a certain it's circular, so it has a certain radius. That circle has a certain radius, and actually we'll see how as this magnetic field radiates out, we'll see how that circle, the radius of that circle, kind of pertains to that in terms of wire. But just don't forget that, okay? Because when we're showing direction, these magnetic fields that are showing up in wires, it's it works the same way. So when we show you the direction, like in terms of the arrow, like we're showing you the north direction and the other arrow south direction, or we say, in or out of the board, right? Those are directional things, and you should be able to associate that with the the north and south pole as well. Okay, so what am I talking about here? So when we have a wire, right? Let's say that we have a wire, red in this wire, or we'll just call it I1. It doesn't matter. And we want to follow this right-hand rule that we're trying to do over here, right? So the first thing we want to do is put our thumb in the direction of current, because what we're going to see, the reason why it relates to over here is this, the magnetic field for this wire is going to kind of circulate around the wire, all right? And so what we want to do is put our thumb in the direction of current, and then our hand is going to be like, it's going to act like that circle that's circling, just like we showed how the magnetic field is circular, right, around anything that's producing that magnetic field. We'll say that's like an iron bar or something like that. Right, well, this is going to circulate around the wire, and our hand, the way our hands are curling with our thumb in a particular direction, is going to be showing us how that mag field is circulating around that particular object. So in this case, our thumb's going to go up, right? Our thumb should be pointed towards the top of the screen, and our fingers are going to circulate around where, right, if we were to, another way to think about this is like, you want to put your thumb in the direction of I, and you want to pretend like you're going to pick up this wire. So if you're going to pick up this wire, you have to put your fingers in on the right hand side first, right? So that's the magnetic field on the right hand side, right? And then the in back, right? In order to pick up this wire or to curl your fingers around it, you'd have to put your fingers in that direction underneath it, right? Or in back. And then on the left hand side, right? Again, if we want to pick this wire up or curl our fingers around it, you would have to then curl your fingers towards you on on the left-hand side, right? And then on the front, right, you would curl your fingers this way. Okay, does that make sense? And so, uh, uh, right, to completely wrap your hand around the wire, right, in front, you would want to put your the front, right, your fingers would eventually curl to the right in front. So that's what we're saying. And like I said, you want to associate with what's going on here. So it is actually, right, it's actually circling right around this, right? We just showed 4 directions of this mag field, but we can see how it's circling around this wire, right? Where, and I'll show you this later, where we can like look at any point actually tangential to that circle, and we'll actually get the direction of B. Okay, because it actually has 360 directions. These 4 that we just got up here, that we just did up here, those are just 4 of the 360 directions, and those are going to probably be the most important ones. You're probably going to have to find every direction, right? But know that that's true. If the magnetic field goes in 360 degrees or circulates around, it must have a 360 degree direction around it, right? Okay, so that's what we're talking about there. Hopefully that makes sense. Oh, and like I said, if you're making sense with this picture over here as well, right? This should be the north, and right, you could look at it like right. That's the direction of the North Pole and South Pole. Now, it's harder to see with these wires because they're just circling around. But if it has a direction, we know how this, right? You can see right in the middle of this iron bar, it goes from south to north, right? And so that's essentially what that's trying to show us. You can think of it that way. All right, does that make sense? Hopefully it does. We're going to talk a lot more about that as we go through. And so, and keep in mind, and we're going to talk about this next, like the reason why this magnetic field even exists in the wire is because the current that's running through this magnetic field, or the current that's running through this wire, what happens is that each charge has its own spin, essentially, right? But what happens is that the charges spin, they align when they move in a current through a wire. So if their spin aligns, their spin is essentially just, that's how we describe a magnetic field of a particle. We say it's spin. Okay, I know it sounds like a top and things like this, but it's not. The spin is directly associated with the magnetic field. Another way, if you want to think of it in terms of how we describe charge, because you kind of can, you can think of spin as magnetic charge. So there's electric charge and magnetic charge, where electric charge is directly related to the electric field, and magnetic charge is directly related to the magnetic field. Right, the magnetic charge is directly related to the magnetic field. Does that make sense? So the reason why so any part like electron, when it's moving around in an atom, it has a magnetic field associated with it because it has spin, what we say. And so it itself has a magnetic field. But when we put that electron in a current where it's moving with a bunch of others, that magnetic field aligns. And what happens is when we run current through these wires, is essentially we're turning them into wires, into magnets, and that's what you should see as well. All right. So let's say we took this same wire. I just want to show you how flexible this is. Oh, I didn't write this over here, but don't forget the step 2 is to curl your fingers right around a wire. Okay. It says around wire. Curl fingers around wire. And so we can kind of do the same thing if the wire, like let's imagine that we took I1, right? So put your thumb in the direction of I1, but imagine we took I1, instead of pointing it up, we pointed it directly at us. So that means current would come right at us. And we would do it the same way we did with mag field, like a dot, right, means towards us, and the X means in. So we're saying, if I'm drawing current in yellow, I'm saying that the current, I turned I1. It's the same wire. It's the same wire. All I did was turn the wire towards us, right? So current is now coming towards us. And what we can see is we can see the 3-dimensionality of this a wire. Here I can kind of just show you with a little bit more detail. So if our thumb's coming out towards us, and this is, believe it or not, what we're about to do is kind of what the second right-hand rule does. But we can use our thumb, put it in the direction of current, and then the way that our fingers are curling right around the wire, this is going to be flipped for the second one, is still our magnetic field, right? Doesn't matter how we're looking at the wire. So again, thumb direction in terms of current, so thumb direction's pointing out at us, so we want our thumb pointing out of the screen. And then keep your fingers flat, all right, well, at first, and then curl your fingers, all right, around the wire. So the wire's pointing out at us, you're kind of curling them, right, in the counterclockwise fashion. So that means that the current, the magnetic field, I'm sorry, for this wire, if we were to look at it from the top, right, would be going in this direction. Does that make sense? Because that's the way your fingers have to curl if your thumb's pointing out of the board. And that's another way to look at it, because you should be able to look at this in a lot of different ways, all right? And then, like I was saying before, and we can kind of use this picture a little bit more, if we wanted to find the actual direction of magnetic field, like let's say we asked you, what's the direction of magnetic field right there? Well, what you would need to do is you would need to draw a tangential line, and then that essentially is going to be the direction of B at that particular point, right? Or if I asked you, like, what is, let's erase this so that we can see what's going on. All right, we know the top is showing us the direction it's going, right? So we don't need to draw it everywhere because it's going the direction everywhere. Let's say like we wanted to know what's the direction to be there, well, we would draw a line tangential. There it's going directly down, right? We can see that. But that's how this works, right? If I wanted to know B at that point, right, you draw a tangential line, right, to that point. Now, we're going to be doing this later. You need to know how to do this. This is important to understand, because that's how we're going to get a direction of, right? So there, I'm sorry, that one should be a little bit better, but you guys get the point. You make a dot at the point that they're asking you where the magnetic field line is, and then you make a tangential line through it. Okay, I'm going to just get rid of that one because that was getting messy. And there's two examples there. Like I said, we're going to do it more. Like at the bottom, right? We can do one more. At the bottom here, if they want to know the magnetic field line, then you got to make sure you're staying consistent with the way you know the magnetic field is going, right? You can see all these arrows are essentially pointing in the same direction. But like there at the bottom, right, the magnetic field, a tangential line would be that way. So that's like B at the bottom, right, in terms of the wire. Kind of didn't really tangent. I mean, you can see it's tangential, but I should. Right, we want you to do it on. There you go. Right. So that would be there. So we can see all the different ones, right? It can be in any direction based off where we draw that point and draw the tangential line. But that would be the direction of magnetic field at any point, because it has, like I was telling you, it has 360-degree points essentially, and that's what that's trying to tell us. So the second right-hand rule is kind of it's pretty much the same one as the top, and that's what the book tells you. It's like except for a wire, it's the right-hand rule for a coil or a hoop. Okay, but I say it a little bit different just so that they differentiate in your head, because when I explain this one the way I do at the bottom, it helps remind you that you can use it in another way, because it's actually later on we're going to use this second right-hand rule kind of as a shortcut. You'll see it's going to be really useful to have in your back pocket. All right, so we say, or what I say is to find current. Oops, sorry. To find current direction with known mag field direction. Okay. Okay, to find current direction with known magnetic field direction. And I noticed I didn't write, right? There should be direction. Should be in there, right? To find magnetic field direction with known current direction. Okay. So this works the same exact way. Like I said, they're almost the same thing. But here we're going to put the thumb direction in mag field direction. And like I said, I'll show you how to use this. And then our finger curl, I'll just write it. All right. And then our finger curl, we're going to curl our fingers. And that's going to be a current direction. Well, I'll show you. That's the right hand rule there, though. All right. So if we have like, let's say I have a wire. All right, and we can apply mag fields to wires, okay, but that's not what this is saying. So let's say for this wire, we tell you that there's a magnetic field because of the current going through a wire, and that magnetic field on the inside due to that current going through the wires on the inside. So what you can do is you can put your thumb in the direction of B. So here I'm saying B is in, okay? You don't have to draw a lot of them. Okay, B is in, okay, that's B. All right, so you want to put your thumb into the board and then finger curl direction. Keep your hand flat and then curl once your thumb is into the board, curl your fingers, and that's going to be the direction of current. Okay, so that's how you get that. And yeah, current direction is 360 degrees essentially here. So, but you don't have to worry about that so much like we did up here. It's going to be important for mag field to be able to look at a particular point in that circle, draw a dot and a tangent line, but you don't have to do it with the current, because that's what we're saying. That yellow is the current, right? So we're saying like I is essentially clockwise here for this one. Does that make sense? And that can go either way, right? That can go either way. Like let's say we have a wire with a current going through it, and we tell you just the opposite, right? We say, hey, the magnetic field's now coming out at you. So your thumb should point out at you, and you're going to curl around, right? Your hand will stay flat as your thumb points out at you, and then you're going to curl your fingers around, and your finger curl direction is going to be, right, going to go like this, like it'll naturally wrap around, right, the B. Now again, remember up top, the top two, we were talking about current direction, so our thumb was in current direction. Down here, that's B, so our thumb is in B direction down here. Okay, I just want to make sure that that's clear. So here we can say that, right, I is it's counterclockwise, right? It's moving in the counterclockwise fashion because it's moving in the opposite direction, all right? Does that make sense? And just note, like I said, these can go, you can essentially, if you look at them, you can see how they're interchangeable, right? Like if I gave you like if I we can do one more here. I'll show you how this one just kind of goes both ways. So let's say we tell you there's a current going through this wire, and at the top it's moving to the left. Okay, so you can put your thumb to the left, right? All right, and that's going to be the direct. Or I'm sorry, I pointed at the wrong one. That was my bad. I'm showing you how this one can also be used for a hoop. Sorry about that. The first one, how the first right hand roll can be used for a hoop. So, right, there's a current running through this wire here, and I just showed you the direction. It's to the left. So put your thumb in the direction of the current and then wrap your fingers around this, and we can see like at the top, our fingers have to go in, so the magnetic field at the top of this wire is going in, and the magnetic field on the inside is coming out. So that's the magnetic field due to the wire on the inside, and that's where, when we talked about the magnetic field on the inside of this wire, that's what we were talking about. So you can see how it can go both ways, right? This is B that we just got from I direction, okay? And it goes vice versa, okay? You can do the other one. I just showed you how to get thumb direction and get current direction from that, okay? So hopefully that makes sense. All right, so since we know how to get magnetic field direction now, right, we want to make sure that we can now solve for magnetic field. Kind of an interesting thing. I don't know if you guys realized it, but we have not yet given you an equation to solve for magnetic field. Like we've talked about force, right? Force due to a magnetic field, and B's in there. B's in there. So if you need to solve, if you have those variables in there, you can use that to solve for magnetic force, the value of it, right? But we never just said, hey, if you have like certain motion, a certain velocity, right? Because that's what current is. If you have a certain velocity, then right, a certain direction of a charge moving, can you, what's the value of magnetic field as it radiates away from that charge, essentially? Because current is just a bunch of charge moving in the same direction, but each one of those charges is radiating out a magnetic field, and that's what we gotta look at when we look at that's the magnetic field that we measure when we're measuring the magnetic field for current going through a wire. So just remember that spin is magnetic field because we talk about that. And when current moves through, right? Oops. When current moves through a wire spin a line, so we say spin of charge, right? Right, and a current aligns. Okay, or remember, spin is mag field, so you can say mag field aligns. However you want to. It means the same thing, right? Mag field aligning, spin of charge aligning. It's all saying the same thing, but that has to stay in the back of your head as we work through this, because that's why this magnetic field exists in the first place, okay? Just have to remember, we don't really relate back to it much. That's why I just wrote it at the top of the page so that we remember, but it's crucial. And just to make sure that, if you ever wonder, why are we measuring this mag field again? The charges, the current moving through this wire, each one of them has a mag field, because each one that spins, talking about the magnetic field, they each one have a spin. So if they have a spin that's trying to talk about their mag field, so and that mag field is going to radiate out, just like electric field, right? Electric field radiated out away from a charge. Magnetic field radiates out from a charge as well, from a moving charge as well. All right, so right when we first look at this, because we're going to give you two. So this is Ampere's law that we're trying to talk about. It's equivalent to Gauss's law, but it lets us measure the magnetic field a certain direction away, a certain distance away from a wire or a solenoid. Those are the two we're going to give you here, right? Where a solenoid, don't forget, and I'll explain it more when we get to it, but it's where we get like a block of iron or something and then wrap just a wire around it with a certain length around it. And anyway, so when we look at this wire, right, we just learned the right-hand rule. So if we wanted the magnetic field direction for this wire, we know that we need to put our thumb in the direction of current, which is up or towards the top of our computer screen, right? And then we want to curl our fingers around this wire, right, in a 360-degree fashion, right? So they would curl around like that, right? Does that make sense? Hopefully you can do that. That's just from the right-hand rule that we just got done talking about, okay? And so that's true at any point in this wire. Every charge moving through this wire, and they're essentially like aligned with each other, right? So we can just like look at like 4 electrons here. All their spins are right, but they're all along this wire all the way through, okay? They're all pointing this way, right? So when we measure one magnetic field, we're measuring the magnetic field for all those charges essentially, or for the wire. Just keep that in mind, all right? So this B, right, it essentially, right, it radiates out because the magnetic field radiates out and from this wire in terms of a circle. So it's circulating, right? We talked about earlier right in the page right before this, how this magnetic field circulating around the wire, and that's exactly how we kind of describe the magnetic field here when we're trying to write an equation about it, right? And so what we do, it's kind of interesting how we kind of break this equation down. But before we look at it, and just keep in mind, like the way this works. So like, let's say so this is the magnetic field, a few lines of the magnetic field, a certain distance away from this wire. So if they told you, hey, what's the magnetic field like a meter, let's say that's where I drew that green dot, that's a meter away from the wire. They say, what is it a meter away? Well, that's some r, right? If these are circles, that's going to be the radius, right? Because that radius is going to pertain to a certain, right, to this magnetic field, right? And so that's the radius that we would want to use in here, and you're going to see how that works, how we get that in this equation. But that's important, right? Or we could say, hey, what's the magnetic field out here, right? You would do the same thing. It would just be a certain r away from the center. Okay, and just keep that in mind. That's just important to remember when we go to talk about everything here. All right, and so and for a solenoid, before we get into the equation here, because for a solenoid, which again, like I said, is wires wrapped around uh, a piece of iron, but essentially, right, it's something, I'm not going to draw the iron, but right, this is, looks something like this, right? You guys are very familiar with what this is. And so again, we know the right hand rule, right? We want to use the right hand rule to look at the magnetic field, see how the magnetic field is circulating around this solenoid. And so we can do that using our right hand rule. So what we want to say is up here. I mean, we can kind of, I mean, I know that picture is hard to see, but I'm going to kind of give you some more orientation. So in the back, we can say, and we would have to tell you this, okay? Or we could give you the direction of mag field, and then you'd be able to tell us. But if we were asking you for the direction of mag field, we'd have to give you current direction. So in the back of that coil, the current is moving to the right, okay? And so if the back, if it's moving to the right, when it gets over here, it's going to be coming towards us. The current is, right? Does that make sense? The current's going to be coming towards us just in that part of the loop. That's the direction of current, right? So in back, it's moving to the right. On the right-hand side, it's moving towards us. Then on the front, the current is moving to the left, okay? This is important because we got to use this for the right-hand rule. If we know the direction of current, so we really just want to look at that red vector, right? That red vector is going to determine the right, that's the vector we want to use for the right-hand rule. Okay, so it's going in front in front of this coil. For all those coils, it's going to the left, right? Because that's the same direction for all those coils that we have drawn there. So put your hand to the left, right? And what you want to do, right? Put your hand to the left. Keep your palm open still, okay? That's important here. You've got to start like that. So put I'm telling you to put your hand to the left. Would you want to do that, I guess? Start with your hand to the left, but then you want to curl your fingers around, right? Your hand should be pointing to the left. I'm trying to get you started in the right direction. I kind of confused myself there for a second. So the front, right? We're saying the current in the front of this is pointed to the left. So point your hand before you start curling your fingers, right? Point your hand to the left, because that's how you want to get your hand oriented before you start curling your fingers. And then your finger should follow the current in that hoop. So you're right, we're saying in front it's going to the left. So in back, your fingers better be pointed to the right, okay? And they should be, right? And then on the right-hand side, they should be coming up as you wrap your hand around, right? If you follow this current with your fingers, right? And remember, as you follow your current with your fingers, you want to keep your thumb sticking straight out. And so when you give a thumbs up, essentially, as you curl your fingers, you're going to give a thumbs up. The thumb direction is going to be your magnetic field direction. And so we see for this wire, it's down, right? And again, if you're having trouble, right, you want to start with your hand to the left, curl, just once your hand is to the left and your palm's open, so your palm should be facing the screen essentially. Just let your fingers naturally curl because you're following the current direction. Once you follow the current direction, once your hand makes a complete fist, your thumb's going to be pointing in the correct direction. If your hand was pointing to the left as you begin and your palm is facing down, your palm shouldn't change direction. And your thumb's going to be B. So that's B here, right? But we want to look at how this circulates around, okay? So because that has something to do with the equation. So B goes this way, so we know it's going to go like this, but right here it's almost perpendicular to the solenoid, and that's kind of important to talk about. And then it's going to come back in here, okay? And so, right, so hopefully you can see that. So that's B direction for this solenoid. You got to be able to get these, okay? And so essentially, like I said, right here, we can see, this is something kind of important, that the length of this solenoid, right, as this thing circulates around, the length of the solenoid, and we can see it on the inside too, right, that the length of the solenoid is also kind of giving way. It's telling us something about the magnetic field. about the magnetic field. That actually doesn't look too bad, does it? About the magnetic field associated with that coil. Does that make sense? Because that's important to see here what we're going to talk about, right? Do you see how it's right, just right there? Everywhere else it's kind of curved, but right there, just the length of the coil, there's actually the magnetic field's almost straight, and we can see it on the inside. So what does it have to do with anything? Well, when we talk about the Amperes law, right, when we go to use it, it's based off of these two things we call circulation. Okay, and there's a math and a physics definition for circulation, right? And this is equivalent to Gauss's law almost, where we use this thing, but it's in terms of we call it in terms of circulation. That's all that's supposed to mean. This sign, but it's a circulation instead of flux, right? I just want to draw it better, and I can't seem to draw that thing well. I apologize. And try it one more time, then I'm going to give up. Okay, there we go. That's better. Where the math definition is telling us B times change in L, where that change in L is just trying to describe the length of the magnetic field. Okay, so if the length of the magnetic field is going to be kind of different for a wire versus a solenoid, okay? So L is going to be a little bit different, right? The change in L is going to be a little bit different for the solenoid versus the wire, all right? So now I will draw that line back in between them, because we kind of need that to start to do the math here. All right, so what we see here is we got to let's first describe the change in L for the wire. Okay, so for the wire, okay, you want to think of it like this. So even though these magnetic field lines, right, these magnetic field lines, they're circular, we know that I could say, like, think about a rope, right? I can take a rope with a certain length, right? Let's say I have a rope with a certain length, and then I take that rope and I connect, right, these two ends, I bring those two ends together. So then that rope ends up being a circle, right? And that circle is going to have a certain circumference, right? And we know that circumference is equal to, right, 2 pi r. So we can see that the change in L, because that's essentially what that is, right? The length is the change in L of that rope, right? When we make that rope circular, the change in L, we can write that here, the change in L for that straight line, and that is like a certain length, right? If we make it circular, is going to be equal to 2 pi r, the circumference, okay? So a change in L for this wire is going to be equal to that, because even though these magnetic field lines are circular, we could essentially imagine like the opposite of this, right? Where we would break those, like we can imagine one of those magnetic field lines is a rope, and instead of connecting the ends, we detach this rope at one point, just cut this rope at one place, right? And then we'd be able to make the rope linear, right, like this. And so that's why the change in L can be that. But these are circular, okay? And so the change in L, the length of these magnetic fields, is directly related, and I was kind of trying to show you that here, right? But is directly related to this radius, okay? These radiuses that are there, it's directly related. So let's make our equation. Sorry. Let's also get our other change in L for the solenoid. Sorry, I got a little excited there. So I'm going to erase this right there because we don't need that anymore. But we can see, like I said, this on the inside. We can see on the inside, and I pointed that out twice, right? Here it's going up, right? But just right there, it's almost straight, right? Pretty much we could say the magnetic field on the inside of the coil, right, or right here on the outside, right over here on the outside, right, or there on the. I'm gonna also erase that because that's gonna play with us, I think. We know those directions. That's how we got magnetic field. Rewind the video if you're confused about that. So we can see inside. I just don't want that it's pretty much straight, right? It's going down versus that one on the outside, right, that I marked over here that's going right? But this one, right, we can see if we look at the 2 points, right, they're essentially straight. All right, so that means that this change in, and that's how we can look at this. So anywhere, right, in terms of this solenoid, we can essentially measure the change in length of the magnetic field in terms of that. And let me draw this a little bit better because those kind of radiate out probably too far, just to let you, because that change in length is really, right, just really, it does describe, because it starts to curl right in. I want to give this more justice right there. So it is essentially describing, right, the length of this magnetic field. So when we look at this, we can see that the L, right, is going to be associated with what's going on here. This is essentially the change in L, right? And we can see that for this change in L, oops, right, we can see that it's equal to something. Essentially, right? These coils are stacked on top of them, so they have a certain length, right? So there's a certain length, right, that these coils, and maybe I can do it in red over here, right? There's a certain length. I'm gonna do that in a different color. Oops. That this coil is, right? There's a certain big L. We use big L for that, right? And that big L is directly related to the number of turns it in there. And if you don't know what the number of turns are, it's related to how many times the current makes a full circle, right? And if you don't know, go watch the torque video. But so we know that the change in L is essentially going to be length per turn. That's what that if we mathematically, and I'm not going to mathematically break that down to you, but that's how that ends up coming out. Okay. And the nice thing is that we can actually do something with that later. So that's going to, so we have our change in L, right? So our change in L, and let me put that in, go ahead and put it, because I put it in red over there, right? Our change in L is equal to this for solenoid, and we know why, because we're measuring the length. It's measured to this for a wire, because we know that even though it's circular, that circular pattern can be looked at lengthwise. Okay, so now what we do is we use Amperes Law. So since these are both equal to flux, we can make them equal to each other, right? And we can essentially say that here, where mu naught works just like epsilon naught for electric field. Okay, so just like we have epsilon naught describing permittivity of free space, this is permittivity of free space. They mean the same thing though. They're trying to describe how the magnetic field kind of like flows through free space. Okay, so mu naught's the equivalent of epsilon naught for magnetic field. So mu naught is the constant that relates to magnetic field. Epsilon naught's the constant that relates to electric field. Okay, but they're essentially describing the same thing for each field. Okay, so that's the next thing. We make them equal to themselves, right? And we know what I is. I is current. And then this is Ampere's law, and we want to solve Ampere's law for magnetic field. So when we do that, right, we see that it's mu naught I over change in L. So what we have to do, we can get an equation for both of these real easy. We just have to incorporate our change in L. We have our change in L. We know what our change in L is. We know why our change in L is what it is. So all we have to do essentially is just put them together in each one. So let's start with the wire, right? So let's put our change in L in this equation, right? That's our magnetic field equation. So we'll start with that. But then we want to put our change in L in there. So when we put our change in L, that makes this equal to, right, our change in L is 2 pi r. So if changing those 2 pi r, that this becomes 2 pi r, right? So this is the magnetic field for a wire, how it radiates. Where that r is this r, okay? Don't forget that. That r is the r of the different radiuses of the different magnetic fields as they, and I'll write it again up here. This is 2 pi r, right? As it radiates out. For the solenoid, right? Which again, the solenoid is where we take a piece of iron and we wrap a wire around it. All right. So we want to put our change now. This change now needs to go in here for Amperes Law. So again, we start with this. Well, it's already there. Why write it again? So we'll just write I know I did it twice over here, but since we have that there, let's just go ahead and incorporate our change now. So the thing that we know, we're going to see something here. So mu naught, mu naught, and then right, n's going to go on top, L's going to go on the bottom because it flips, right, if L's on the bottom, and then I. But we know, so little n, we can describe n over L as little n. So every time you see little n in this equation, that's what it's standing for. So we can just make this look a little bit nicer by just saying mu naught little n I. But remember that little n, and I'll do it in red, but remember that is another, let's do it in blue. That is another variable, or it's this one over here, little n. Okay, so either one works, but these are the equations for a solenoid. All right, so now you know what it is. That's again, so that's how you solve for the value. If we asked you for the magnitude of the magnetic field for either one of these, you should be able to tell us, okay, what it is. Okay, all right, because these B's, these equations we just got you are the equations that get you it based off the shape that you're using. Okay, so let's practice this just real quick. I don't want to spend a lot of time on this because trust me, there's a ton of math to it, but I don't want to get into it, all right? But I just want to show you how to incorporate your right-hand rule. Now for this question, you have, in terms of your givens, I'm just going to write them up here. Okay, you have everything. You have every number, just so you know, every number you need, or maybe I should write value. You have every value except B net, and that's what we're looking for, is B net at a certain distance. Okay, so they tell you how distant, that'll be R, but they give you that distance. They give you everything. You have every number in this picture we're about to draw except B net. We're trying to solve for B net. They want to know what's the net B, like 4 meters away from these 2 wires. So we have these 2 wires. Okay, one of the wires, the current is coming out at us. Another one of the wires, the current's going in. Okay, and like I said, they ask us, okay, so what's the magnetic field at some distance? We'll just say that, and then they tell you, right, they give us the R's. They also give us the distance between these 2, which means, right, sorry, I just noticed, because the wire's on the inside, I just drew the circle around. The circle isn't the wire. I want to make sure that that's correct for you. Right, so we know the length between them. So we also know we could have the length if we needed to make a triangle or something, hint, hint. All right, so just the point is, again, you have every number you need here, right? But let's say that this is some L here. Oops. Okay, so they're a certain distance apart, and we want to know the magnetic field a certain distance away. All right, and like I said, everything's the same here. You know current value, you know everything you need to know about these questions except B net. All right, so in order to solve this, in order to start to get net B for any type of wire, whether it's a coil or anything, okay, you want to go ahead and you want to start by using your right hand rule. to get the directions of B for both. So we'll call this I1 up here, and we'll call this I2. We need B direction, so it would be B1 and B2. We need, excuse me, we need those directions, okay? So the first thing that we do is we use our right-hand rule, right? So for I1 sticking out, right? We can write that, make sure that you, in case you don't know, and I2 is going in, right? That's their direction, right? So if we do the direction, right, if we put our thumb in the direction of I, which is sticking out, and then let our fingers just naturally curl around our thumb, essentially, right? Or we put our thumb in the direction pointing out and keep your hand completely flat, and then let your hand curl, right? We can see that B is in this direction, right? That's B1. That's the direction of B1, right? Which means that it's going, it's counterclockwise, right? B1 is counterclockwise for I1, right? And then we want to do the same thing for I2. So put your thumb in, let your fingers naturally rotate around this one, and they should naturally rotate. If your thumb's pointing in, the only way your fingers should be able to curl is clockwise. And so we know that B2, right, is going to be clockwise. Okay, so these are our directions. We have our directions of everything. And again, if you're not too sure about that, it's just practicing the right-hand rule. That's what we did over here, okay? We put our thumb, it's the first one. We did this one up here, the first one. Thumb in direction of current, then we curled fingers around wire, and that was the direction of mag field, okay? So now that we know the direction of mag field, we got to find the direction of mag field here. We want to know what B net is there. All right. So what you have to do with this, it gets a little tricky here because you have to see some things, right? First, you have to see that because the center radius of this circle should never change. So we see that the center radius of this, as this, because these this mag field is going to radiate out, so these circles are going to get larger and larger and larger, right? That's what we said here with this wire, right? You can see that those R's are getting, those fields are getting larger and larger and larger. So we know that, so we got to kind of keep account of that. So we know that that should be the center of our circle for the magnetic field for both those currents, okay? And so it's up to you how you want to do this, all right? But well, I want to make this a little shorter. You'll see why. Well, it's up to you which one you start with, but make sure that you're drawing your picture, you know, good. And this is where it gets a little tricky, I will say. But try to imagine, right, that you're so something like that, where we can see, because this is supposed to be where it's essentially the fattest, right? So, right, if I did this right, right, oops, I'm really doing this bad, right? We can see that this is essentially supposed to be curling in. Again, I'm not the best artist here. I'll try one more time, but hey, that got worse. Okay, I keep drawing that as the fattest part. All right, kind of like that, but we can see we can see that there we go, that's better, right? Because this would be the fattest part, so we could see, right, this should be the fattest part of the circle right here. Geez, I did that pretty well. And so essentially that line should have came through this point. We can well, just imagine that line went through that point. It would be essentially the same point. So what we want to do, like I told you, is draw, right? You draw a point at that line, then you draw a line tangential, right? So we can see that the B at that point is essentially in this direction, right? That's B1, okay? Now we want to do the same thing so I erased it. You can go back and rewind if you need to see that. But I need to erase that because I need to draw now another circle, but the fat radius, right, needs to be in relation to the one on the bottom, right? This one I always have a little bit more trouble with, but, right. That's close enough. So we'd want to do the same thing here, but we can, let me do that better. Let me do that better. All right, that's as good as it's getting. So we can see if we drew a line right here, right, and again, we have to remember, I didn't show that for B1, but I'll show it here to make sure that it's clear. We also have to remember the direction it's moving, because, right, B1 is circulating counterclockwise. So over, if I look at it over here, B's moving in this direction. So that's why B1 should be pointing up, because if it's somewhere over here, it's pointing up B1, okay? So B2, right, we know is circulating in the opposite direction. So if I draw it on this circle, now again, I'm going to erase this, but it's good to draw on this circle so that you can see the direction you got to draw your vector. So current, right, or the magnetic field's going that way, so that means our tangential line, when we draw our tangential line here, it needs to go tangential in terms of this. Does that make sense? So that is B2 direction there, all right? All right, because it's tangential to the. That's as good as it's getting. I know you guys understand what I'm doing. It should be kind of more circular there, and you draw a dot and do tangential. But that's what we're saying. So now I'm going to erase this green because it's going to just get in our way. So we can see, right? And if I did this correctly, this spot should actually be crossing right here. Okay. So it was the way I had to draw my things. But we see the directions of B essentially. Let me just do this so I can make that right, believe it or not. Okay, and so because I want this to look right for you. Okay, so that's the point we're looking for, and you would go about it the same way. I'm just redrawing it because, right, I would need to be some kind of math or some drawing genius to be able to draw that perfect, but you guys saw how to go about it. You draw the tangential lines of the circle. It's a little bit complicated. That's why I'm showing you how to do this here, right? And again, these are going to be a certain distance apart. Nothing changes, right? I just want to make this more to scale so that it makes sense to you when you're looking at it. Okay. All right, and so we know, right, if we were to actually look at the R's, right, the R that we actually need, right, is right here, right? That's the actual R because that's the distance to that point. But we also know, right, we already said we know these distances as well because of that L. So we kind of know, right, we know, and like I told you, we gave you every value. We gave you this theta. It's important to know that theta because when we look at how these intersect, that theta and the theta for those components are going to be the same. All right, so hopefully we're on board. Everyone understands. If not, you can rewind and look. But again, we're just looking for B net right here, and we just got the vector direction. Okay, so the next thing we want to do, I'm going to draw that smaller, is just kind of, we want to redraw this, okay, because that's a little hard to see there. Okay, so what you want to do is you can redraw this in terms of just, right, X and Y components or X and Y coordinate, right? Because we can see that we could put a Y coordinate and an X coordinate on this thing, right? Essentially put like a graph, like I'm drawing right there, like this on there, right? And so I'm trying to, what I want to do is just draw this picture on a graph, okay, because we can essentially see how that is, right? If this is negative Y down here, this is positive Y up here, right? So this would be positive Y, this would be negative Y, this would be negative X and positive X, okay? The stuff we're used to from physics 1, right? And so when we draw these vectors, right, we see that B is like this. We see that or B1, right? We see the B2 is like this, okay? And I'm going to move this because I'm going to need that spot. And so what we want to do, the first thing we got to do, since this is at an angle, is we know we got to add components because since B is a vector, these components matter, right? And so when we draw these components, right, the first thing we do is we want to draw the y component. So that's the y component for B1. I want to draw the y component for B2. Okay, so this is by, oops. This is by2. This is by1. As you can see, they're in opposite direction, and you guys should be well enough familiar with vectors to know what that means. And then we can see that b1x and b2x are in the same direction. Okay, so that means that those are going to add. So we shouldn't have to get into it here, okay? You should clearly see that this right here, in terms of the y, we shouldn't have to get into it, that since they're opposite, the vectors are in opposite direction, by2 and by1, they're just going to cancel. So we don't even need to write an equation for those. If you want to, you could say by. If you wanted to, you say, oh, by net is equal to 0, and you can show how they're subtracting, I suppose. But we're really just concerned with, since b2x and b1x are both pointed to the right, we can see that. These are their tips here, right? That they're going to add. There's going to be an additive, and that's going to be the direction of the B field. So we already know the net B field is going to be, right, in the positive x direction, because that's what those vectors are telling us. And then if we got to add them, we know what to do. We know the equation to use. It's this equation, right? There's two wires, so we know that we got to write that equation. We just have to keep in mind, right, since these are vectors, that they have components, right? There's an angle in there. And like I said, don't worry about the math, but it's this angle here, this theta in here, and the theta between that's in here, they're the same angle for they're the same angle for the same reason, like a box sliding down a ramp, the angle between the components there and the angle of the ramp are the same. This is the same reason, okay? So those are the same angles. Just take my word on it. I'm not going to prove it to you because you should know why already, all right? So we know that right, if we wanted to generically write an equation for b1x, right, we would have to, it would essentially just be b sine theta, right, because it's it's opposite of the bx component's opposite, and it'd be the same thing for b2, right? b2x is also going to be, right, but it's b2 sine theta. Let me write that better. I'll just write it. b2x b sine theta, right? So we know essentially they're generic values. We just got to pump in the b, right? The b in there for both of those is going to be equal to this, where r is going to be, oops, sorry, not that r, these r's, but those r's are the same, right? R1 is equal to R2. Okay, and we'll say I1 is equal to I2, but you have these numbers, so it doesn't matter. Even if I1, all right, I1's determining the magnitude. Don't get me started there, but that's what I'm telling you is going on in this question. Okay, so now just to write an equation, right? We know that this is our generic b1 x sine theta and b2 sine theta. Those are our generic equations. So we essentially can say, okay, b net is going to be equal to bx, oops, b1x plus b2x, okay? And then we know that it's going to be, right, b1 sine theta plus b2 sine theta, right? And so since we know those things, right, then we can just now fill everything out. So it's mu naught I over 2 pi r sine theta. And remember, if this is B1 that we're talking about first, then this needs to be I1, because B1's coming from I1. And you need to label these as such. If they're not labeled, you will not get points, because we're going to ask you, what I is that? And if it's B2, then you need to label, B2 is coming from I2. So make sure that when you write these equations, you're writing the appropriate current. Okay, so I2, right? B2 comes from I2, so make sure you do that. That's all I'm trying to say. All right, so that's how you do that. Hopefully that made sense. If not, you can send me questions and ask me. We got to get moving on to the next stuff, which is pretty straightforward, actually. The rest of the stuff isn't bad. So let's get going on that. So since we know that these wires have magnetic fields around them, right? And we know that if we get two wires next to each other, there's going to be, their magnetic fields essentially are going to interact with the currents in those wires and cause a force. So before we get into that, let's just review everything. So we just write, first, let's just write the magnetic field equation, because we need to have that in our head. Then we got to then we want to make sure that we have the appropriate current, or the FB, equation, which is, right, that's essentially how we write the cross product. But if we needed the number, which is also the cross product, it's just, I guess this is how we get them. One of them is for the right hand rule, I guess, right? And the other one is like to get a magnitude. This one with the sine theta, right? Those are the different ones where right, you can't forget that this angle, right, that's the cross product angle, and the angle is between L and B, and L is the direction the current's going, okay? Don't forget that. And because this sine theta is associated with B, just another way to write this should be in the back of your head, should be B perpendicular. If that sine theta was associated with L, we'd write L perpendicular, right? So we always want the magnetic field perpendicular to L, is all that's trying to say, if we're going to get force. And that's what we get. That's what we end up getting with these. Anyway, so let's practice the force on a current before we start to practice how the forces on two wires are going to interact. Let's just practice how an applied magnetic field to a single current acts. Okay, and that just means we're going to use the right hand rule up here, right? So that means that this is going to be our hand direction. That's what we say. B is going to be our palm direction, right? I just write P, but that's palm. And FB is going to be our thumb direction after finger curl. So once our palm's in the B direction, we give a thumbs up, and our thumb direction is right. That's the direction of FB, right? Now, keep in mind that we talked about this, and if you don't remember, you can go and look at I believe we talk about it when we're talking about Hall voltage. We explained to you why the FB, because current in a wire, right, positive and negative charge move in opposite direction in a wire if it's current. They don't move in the same direction. So because of that, FB, in terms of current in a wire, FB is going to be the same direction for either current. So there's no hand flipping here. You're not going to do it one direction, say, oh, it's negative, so I got to flip my hand like we did with the last FB on a single charge. We prove that to you in that part of you can look in your book or in lecture. We prove that to you already when we're talking about Hall voltage. But you already know current in a wire, when current's moving, you learned this in chapter 18, that positive charge move opposite direction and negative charge. So if they're moving in opposite direction, this FB, right, in terms of having to flip our hands, it makes sense that it's actually both in the same direction. Okay, but just know that there's no hand flipping. No hand flipping for this one. It's just gonna always, it's nice. It works a little bit easier. So let's practice this a little bit. So let's say I have a wire, right? And remember that if that's the wire and I tell you that the direction of that is the direction of current. Now, yes, I know this wire. If we wanted to use a right hand rule, thumb would go up. We'd wrap our hand around this wire and say, hey, this wire has a magnetic field. Well, if this wire is going to feel force, it can't have a force applied to it from its own magnetic field. It'd be like, imagine trying to pick yourself up. You can't do that, right? So this magnetic field can't really affect the wire that it's coming from, right? The current there is the source of this magnetic field, right? And so that's not the magnetic field that we want to be looking at when we're looking at force, right? So every time we put these wires in a mag field, we call that, essentially we can call that like an applied mag field, right? Because that's the So that's B applied essentially. And that's a mag field that's being applied to it. It's not its own magnetic field because that current has its own magnetic field, right? So I'm going to erase this because I don't want that to get confusing, right? And also keep in mind, remember, we used to be able to trick you with the last right-hand rule, right? Like if the particle, we tell you, if you place a particle in a magnetic field, we would tell you there's no force because that particle has to be moving. But remember, if this is current, if there's current moving through this wire, even though the wire isn't moving, the charges are moving through the wire. So if the charge is moving and that's charge moving in a magnetic field, there's going to be force. So the wire doesn't have to be moving because the charge is moving. The charge is the current and it's moving, right? Where before we had to actually have the charge, like when it was individual point charges, we needed to be moving that point charge. All right, but here the point charges are moving through the wire. All right, so let's practice this right-hand rule of currents going up and the B applied. So this is the B that's everywhere. It's sitting in this magnetic field. It's not the magnetic field that it's producing, right? Then we want to start by putting our hand up towards the top of our screen, right? That's L direction. That's what we talk, right? Current direction or L direction, up, right? For this wire, because they're telling us. And then palm direction needs to go in because the B applied is into the board. And then you give a thumbs up, right? Curl your fingers and give a thumbs up, and you see that this way is F. So this is FB on this wire from this magnetic field. And this is where things start getting a little important with the equation. So if we need to write this equation, we should write this equation. If this is I1, this current, it would be I1 L1 because it's the length of that wire too, right? That's what we're talking about. And then, but the B is going to be B applied, right? Like that outside B. Okay, so right, make sure that you can write these equations for these situations. It's very, very, very important that you're just not like doing right-hand rules. Okay. So let's practice this a little bit more, just a few more, and then we'll move on. We're almost done. Just a little bit left. Once you have this down, we're gonna do one more thing, and it's gonna be really, really, really straightforward. Okay, so let's just say, right? So that was our first example. Let's just say that I have a wire. Let's say the wire is pointed at me, so that's current now. Okay, and well, let's keep the colors consistent here. So I drew the wire black up top. So let's say the wire, right? The current is coming at us. So that's current direction. It's out. Okay. So, and let's say that it's in a B field and the B field is to the right. All right. So just keep in mind how this works. So now your hand should be, and they want to know force on this wire. So your hand should be pointed at you, right? Because that's the, in terms of the right hand rule, that's the first one. The hand goes in the direction of current. Palm direction is B. So if B is to the right, then your palm should be facing to the right, right? So your hand should be pointing at you and your palm should be facing the right, and then give a thumbs up, and FB is up. Okay, and again, from the last time, if these are, so B is perpendicular to I already, right? B's in the X, I's in the Z. So there's going to be FB, right? Don't forget that trick. There's FB when the first two are perpendicular. If we tell you FB's in the X and B's in the Y, then that there's going to be an I because that FB is real and it must be perpendicular to all those, right? Or if we tell you I's in the Z and B is in, or that's what this one, if I is in the Y and B is in the Z, FB's in the X, okay? And don't forget the things we can trick you on, right? Like what if I tell you, right, that B applied is into the board. Oop, I didn't call that applied, but that's what that was down there. I should have, because I'm trying to stay consistent for you. That was B applied there, right? And so let's say B applied is into the board, but let's say current is out of the board, right? Well, the sign between those, right, if we have the equation, right, the sign between L and B is 180 degrees, right? And so 180 of sine is 0, so 0 times all that, FB is 0, right? Because they're in the same direction. They're not perpendicular. So you already know if things aren't perpendicular, there can't be an FB. So if B applied is to the right and current's to the right, there's no FB because those two weren't perpendicular. You already know that answer already. You don't have to go and find the angle. Because if they're in the same direction or opposite direction, right? If they're in the same plane, I and B, there can't be FB. And that's really the point of that, all right? Okay, now like we said, if magnetic fields affect wires, right? If a magnetic field can have a wire, then can apply a force to a wire, right? That wire will feel a force from that magnetic field. Then when we put two wires next to each other, they're going to affect each other because, as we've been talking about, they both have magnetic fields, right? And so when we and that's this last thing we want to talk about here. But when we describe that, right? So let's say we have these two wires sitting next to each other, right? Well, right, if we want to do the right hand rule, our thumb would go up and we'd wrap our hands around these wires and we could see, or our fingers around these wires, and we see the direction of the B field, right? But we see that we know that we've already talked about, right, these are a certain distance away, but we've already talked about how this B field just radiates out and out and out and out. So there's going to be a point, right? There's going to be a point where where the B field from those wires are going to directly interact perpendicular with each other, right? So like I1's B field, which would be B1, is going to interact with I2, right? And B2 is going to interact with I1. Is essentially what's going to end up happening, okay? And so, right, whatever radius that is, because those two magnetic fields we have those aren't big enough. But eventually, right, there's going to be one from this one that's going to directly interact with that one, right? And there's going to be one from right, so that's B1. Right, and there's going to be another one from this one that's going to directly interact with that one, right? That's circling around, and that's B2, right? And so the distance, right? We see the distance actually becomes now I didn't draw these wrong. I should probably draw those better because, right, the distance is supposed to be, there we go, is supposed to be the radius, okay? And so, we can see that the distance between actually becomes the R for these, right? And so we can still use that magnetic field for both of them, right? Right, the one that we have. Oh, yeah, at the top of the page, I forgot. This one up here, right, will still work where that R, right, is going to be this R that we're talking about in between them, right? And then we can look at direction, right? If we know that they're both circling, right, in a certain direction, then I know that for B1, right, for B1 over here, the direction is going to go into the board where it's interacting with I2. And for B2, right, this is B2 here, I know that when it's interacting with I1, it's going to be coming right out of the board right there. So those are the directions of magnetic field that are actually interacting with these. So that's what we got to do, okay, on this next one. All right, and we're almost done. This is the last bit, okay? So let's just make sure you understand this. Now, and this can get complicated, okay? Just keep that in mind. Like, it doesn't have to be just like two. Like I could ask you about right? Like I could say like there's a hoop and then a wire next to that hoop, and this process we're about to go through works the same way. I'm using a simplified model, right? But these both have current going through it, so they both have magnetic fields. So these two things are gonna, right? They're gonna affect each other because they're both gonna have their own, right, magnetic fields that are gonna be interacting with one another. Okay, so it doesn't matter the shape of things. We just use these two wires as a simple model. So we have these two wires, okay, and they're next to each other. And the question would ask you, how are these two wires affecting each other? That's the question. So the first thing you have to do is you have to use the right-hand rule to get the magnetic field directions for both of these, okay? And these are right, there's only so many directions we can do here, right? So you keep seeing this is in the same direction, but no matter what direction this is just as simple to do, all right? And we've done a lot of different directions as we've talked here, so. All right, so the right-hand rule. So we know, right, let's label some things up, right? We'll call this, right, I1, and I1's going to have a B1. We'll call this I2, and I2 is going to have a B2 that we're going to draw, right? So we're trying to find B1 and B2 direction based off the current. So our thumb should go for I1, and your thumb should go up towards the top of the screen, and then your finger should curl around the wire like you're going to pick it up, right? Now, when you're drawing these magnetic fields, right? Like, yeah, you could do that, but that's not helpful at all, right? How's that going to help you in terms of solving this question? So what you're really trying to do is you're just trying to find the magnetic field in terms of orientation of how these wires are applied, right? So like since these wires are sitting on the left and right of each other, we're just concerned with the magnetic fields on the left and right of both of these wires, okay? But if I had like two wires that were sitting like this to each other, well then I'd be concerned with the magnetic field on right. If this is I1, I'd want to know the magnetic field up here, and I'd want to know the magnetic field down here, right? Or on the top and bottom, essentially, is what I should say of both of these, right? Because in terms of these wires orientation, that's how they're sitting. So if they're sitting one's on top of the other, you need the magnetic fields for both wires on top and bottom of the wires. If the wires are sitting next to each other, like we see here in this question, then you want the magnetic field direction just to the left and right, since these wires are just sitting to the left and right of each other. That's all we need, okay? Don't worry about getting 360 degrees. So you put your hand, right? What we really need is just the left and right. So if I'm going to curl my fingers around this wire, really what I'm going to be doing is putting my hands in on this side. So that's B1 on this side, and put my hands out on this side. In the back, it's going to go to the right. And remember, we talked about this. That's what this was doing, right? We said that several times up here. We talked about, right, all these different directions. We're just looking at left and right. Okay, so the left, it's going in, back it's going, or on the top, or on the left, it's going out. But in the back, it's going to the left, and on the top, it's going to the right. We know that, but we're not concerned with that. So that's B1 direction, right? Now we want B2 direction. Okay, so let's do that in a different color, right? So we'll kind of label these up. So if we do B2, right, it's going to work the same way. Our thumbs should go up, right, and our hand's going to curl around, but we don't care about every direction, just the ones on the left and right. So we know if we're going to curl our fingers around this, right, it should go in on the right and out on the left, which is no different than the other one. They should be the same. If they're not, then you've done something wrong because the currents are in the same direction. So that's B2 direction. Does that make sense? So now we have B1 and B2 direction. So now we know what the direction that's going to be applied to each one, right? We know the direction of B2 on I1, and we know the direction of B1 on I2. Okay, we know these things because of what we just got. So now we want to write them, right? So the way you figure out which one, because there's, right, each one of them has like two, right? Right, and I think it's pretty straightforward that you pick the one that's closest in orientation. So this side right here is closest in orientation to this wire, right? This side's the closest in orientation to this wire, right? So those are the directions, right? So this is the B1 direction we want, right? This is the B2 direction we want because they're the closest in orientation to the wire that they're affecting. So like I told you before, when we write applied B field, we write it at the bottom of the wire. As you can see how this is going to get tricky. So B2 is affecting I1, and we said it's going to be this direction coming out, right? Because it's closest in orientation. It's closest in orientation to that wire, okay? So it's going to be coming out. So that's B2, okay? And then we know B1, right? B1 is coming out, right? Or going in, sorry, but it's going in closest in proximity to I2. So we know that B1 direction in terms of how which direction is closest to I2, we can see that the end direction of B1 is closest to I2 in terms of relation. Okay, so that's how you do that. All right, I'm going to erase that. So now we have the directions. Now we have the directions of the magnetic fields that are affecting these currents, right? So now we can get force. Okay, we should be able to get force. But we should write an equation before we get force, because that's going to help us kind of remember what we need to do. All right. So first of all, let's get magnetic field right? So we got these magnetic field directions. Let's get their values. But we know their values are really easy, right? It's really just this equation, right? They're not at any angle like we saw in that complicated equation. They're just sitting directly across from each other. But we want to make sure that we label everything right in it, right? So we know that B1, right? If we want the value of B1. Now we know B1 is coming from I1, right? We know this is I1 here, right? And we know that B1 is coming from I1, all right? So when we write B1 equation over here, right? We got to remember that it's coming from I1, okay? But that's the value of B1 over here, not near I1. B1's going to have a certain value over at I2, and that's the value we need for the force equation, right? So B1, right, it really is, right, just going to be mu naught I, but we want to make sure we label everything, right? So R is going to be, right, R is going to be the distance between these two wires, right? That's going to be R in that equation. But what's I? Well, we just said I needs to be I1. That's very important, because if you don't tell us what I1 is, you're going to get it wrong, or we're going to not give you as many points as you should get, because we're going to say, well, what is it? B1? Like, it's not just I. I is going to mean something. Okay, and so that's going to be the value of B1 at I2. Okay, that's important. It's an important equation right there. Okay, and then B2, right? Because that's the value. That's the value of B2. So B2, right? If we want to write the equation for B2, well, it's just as easy. We just got to make sure we label it up, right? It's going to be mu naught, right? And then I, but I what? Well, B2, the source of B2 is I2, right? And so we just got to remember that. Now the R's are going to be the same for both of these, because they're right, but the current isn't. So that's how we get the value for B's for both those at that particular distance away from each one. Just remember, B1 is coming from the I1, right? All right, don't forget that. Why did I draw that like that? All right, B1 is coming from the I1. That's the source, right? And B2 is coming from the I2. Just don't forget that, all right? So now we can go ahead and write an equation for the force, right? So we know generically that the force between these is FB, again, generically IL B sine theta, but we know that the everything's perpendicular here, so that sine theta is just going to drop off, right? L's B is in the Z. If you're like, how do you know they're perpendicular? Well, I for both of these currents are in the Y, and B's for both of these currents are in the Z. So, right, I is in the Y, right? B is in the Z, right? I want to make sure you can see the difference here on B, but right, B is in the Z, and right, and B1 is in the Z. So they're perpendicular, right? Y and Z, those are perpendicular. So we know that the angle between this, right, is 90. So that just becomes 1. So we know that, and that's true for both these, right? What we're doing right here is true for both these. So we can go ahead and just write for both these generically, BB is equal to I, L, B, but we got to label it up, right? So this one too, BB is equal to I, L, B. We don't have direction yet, but we can still label these up, because actually these equations are going to tell us how to get the right-hand rule, right? Because the right-hand rule is also going to be what? FB is equal to I, L cross B, right? And the same thing over here. So let's make sure that they're labeled correctly, right? So for the FB over here, what we call 1 to 2. So we're going to call this one, and this one we're going to call 2 to 1. Okay. We can see that for the FB over here, if there's a force on this one, well, it's a force on I1, right? So this needs to be I1 in here, because that's the current that's filling the force, right? But the B, we said the B is B2. So we just got to remember that that's labeled B2. All right, so those are our equations, and we're done with that side. These are correct, okay? That would get you the magnitude if you know those numbers, and that's going to get us the right-hand rule. And then for FB 2 to 1, we just got to do the same thing, but we got to remember, it's I2 that's filling this force, so this needs to be I2 here, right? but remember, they're feeling the force because of B1, because of the other current, right? And so that should be B1 in this equation because it's B1 that's affecting I2, right? And so now we can use these, right? These are the equations, and we can use the bottom one that we have for both of these to get the right hand, which is the right hand rule, right? So let's do that. So let's do it for I1 first, right? So for I1, we want to put our hand up towards the top of the board, right? But B2, that's the one we're using, right? We're using B2. So B2's coming, right? B2's out, right? This one's in, right? B1's in, but B2's out, and B2's affecting I1. So for I1, we got to put our hand up, but our palm needs to come out because that's B2 direction. And when we curl our fingers, we see that F, right? F is going to be, let's do that in a different color. F is going to be to the left, or to the right, sorry. That's going to be F1, 2, all right? And then if we do I2, put your hand up towards the top of your screen, but now we got to remember B1 is affecting I2, and B1 is in to the board, right? B1 is in, so we want to put our hand up towards the top of our screen, and then our palm should be facing towards the screen. Give a thumbs up, and we see F2 to 1 is in the same direction. Now this is telling us something, believe it or not. This means that they're attracting each other, not pushing away. And those forces, no matter what the current is flowing through these, even if the current was different in each one of these wires, like they had different magnitudes in each current, those forces would still be the same because of Newton's third law. This is just like kind of like gravity in a sense. They're attracting towards each other. That's what those forces are telling us. All right. And there's a concept here. Okay. So believe it or not, what we'll see, and I'm not going to prove it to you, right? But the concept to remember here, right? When current is in the same direction, force is attractive. Okay. But when current is in opposite direction, force is repulsive. Okay. Right. So does that make sense? Hopefully it does. All right, because you can prove that if you do these the other way. I'm not going to, right? But what you should see is something else. So we said we turn these wires into magnets, right? Well, we can see and I've told you several times before, but where force comes from is actually the interaction of magnetic fields. So when magnetic fields interact, there's a change in the magnetic field and a force is applied. So there's forces here between these two wires because their magnetic fields are applying. But what did we say about magnetic fields? Right, magnetic fields mean that object is magnetic. Right, so B1 is telling us that I1 is a magnet, and B2, right? Since I2 has a B2 has a magnet, it's telling us I2 is also a magnet. So the current, those two wires are magnets, right? Does that make sense? That's how we know, because they have magnetic fields. They can't have magnetic fields and not be magnets, right? Well, what do we see with these magnetic fields? We see that B1, right? B1 is into the board, right? We see that B1's into the board, and we see that B2's coming out, right? So they're in opposite direction. And what did we say? I don't know if you remember, but over here at the very beginning, right? That directionality kind of means something. So if they're in opposite direction, it's kind of like saying, okay, well, I have a north pole and a south pole here, right? Like we know the magnetic field kind of goes this way, right? And what happens if these are two separate magnets, what happens if I get them close enough together? They're gonna what? Attract, right? Because they're opposite poles. What happens if I have two north poles like this, right? Well, they're gonna repel, right? And why is that? Because, right, this is the B field for that. This is the B field for that, right? The B fields are in opposite direction. They repel. Well, for this north, right, the B field's in that direction, right? For the south, uh, 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 essentially the B field, it looks like it's in the same direction, but we know it's opposite direction. We know another way to look at this, because I know that's kind of confusing. The way that look is because we said this at the beginning too. maybe I should just go to it, is that it comes out the north and into the south, right? So we know that in terms of, if we just looked at a south part of the magnet, the magnetic field's going into it. We know that if we just looked at the north part of a magnet, we know it's coming out. So we know the magnetic field for the North Pole and the South Pole are essentially going in opposite directions, because this is going in, right? The B field's going into the South Pole here. And for the North Pole, right, for the North Pole, the B field's going, it's radiating out, right? So those aren't the same direction. If the B field's going into the South Pole and out of the North Pole, those are not the same directions, right? So we can see, right, and if you want to take that over here, because that sounds like I'm saying the same thing over here, so kind of ignore what I said there. And more importantly, we could say, well, I know for the north, the B, right, the B's coming out, right, is in that direction. And then if I had another north, right, the B's radiating out. So we actually know that the B's in the same direction. That's probably a better way to explain than I was up there, for two north poles, right? So that's why when we bring those two north poles together, they repel. The forces, they repel themselves, right? But when we bring these two, this north and south together here, right, we can see that they attract, okay? And it's because of this, right? We know that the North Pole has a different direction than the South Pole, okay? But, right, or like south, if I had south and south, that still works the same way, right? South, the B would be going towards it, but here the south would be going towards it. The B's in the same direction, so they would repel, all right? So that's where this is coming from. If we're turning these wires into magnets, then if they have opposite magnetic fields where they're interacting, they should attract, right? Because that's like saying north and south are facing each other and they should attract. But if they're in the opposite, like let's say if we did these and like they were both in, on the inside, they were, the magnetic field was both in. So let's say that was B1 and B2. Well, that would be repulsive, because that's like kind of saying like two north ends are facing each other, okay? Or if they were both pointing out, that'd be like saying that they're both, you know, two south ends facing each other, something like that. Does that make sense? Because you should understand why these are repulsive. We turn them into magnets. And if they have opposite magnetic fields where they're interacting, well, then they should attract, because we know opposite poles attract, and that's what this means here, okay? So hopefully that was helpful. That's it. I'm done. That's what's going on here. Hopefully this was super helpful. You can go back and you know, go through the rewind this video and watch what you need to watch, but make sure that you do kind of understand what we talked about in terms of right-hand rule, in terms of the way that we get the magnetic field equation and Amperes law, how to net magnetic field, right? There's easy ways, and then there's this really complicated question we did. And then when wires start to come together, there start to be forces applied to them that we can start to solve and look for, right? And then if they're becoming magnets, right, then we know that essentially they're going to be attractive or repulsive if we're essentially turning these wires into magnets. So again, I hope this was helpful. I'm super proud of all of you. I think you guys are rocking the crap out of everything. And I cannot tell you how resilient and how amazing all of you are. You really are just really, really amazing people. And you make me so proud. Like I feel so lucky that I get to work with such amazing people like this. Not a lot of people get this chance. Like you guys don't realize it. This is a very unique opportunity that I get to be able to work with you students, you wonderful, brilliant students. It's right? Not many people get this, and I just feel so lucky. So just thank you. I'm proud of all of you just for being who you are, but you're all going to change the world. So that gets me even more excited, because I'm going to be able to say, I know them. When I see you guys, I'll be like, I know them. And I'm going to get really excited. And then if you're doctors or dentists, I'm going to come find you and say, you can give me free healthcare or dental care, right? I'm teasing, but you guys are all really amazing. I'm proud of all of you. No matter what you're going to do, you're going to do magnificent things. All right. I will talk to you soon. Hopefully this was helpful. Have a good day.